Hi, this is part two of lecture for MOS transistor theory. And in this lecture, what we will do is we'll try to derive the relation that predicts the current in the transistor, and this is IDS. Um, and just to uh, review what we have done before, we have found out that the current through the transistor is a function of the VGS, the voltage on the gate, and VDS, the voltage between the drain and the source. This is typically the voltage on the gate forms the channel, right? And this channel will have charges inside it, electron charges, and the VDS is in charge of moving these electrons through the channels. So what we will do, we will try to estimate the charges in the channel and estimate the time for the charges to cross the channel, right? And this is how we will derive IDS. Now it's important to understand that the voltage on the gate is what forms the charges in the channel. And the voltage between the drain and the source is what pushes those charges from the source, the electrons from the source to the drain. Okay, so let's try to estimate this relationship. Well, first of all, what we want to do is to estimate the charges in the channel. Okay, so this is another this is a drawing of the transistor right here. This is our source, our drain, and when we establish the channel, there will be electrons right here in the channel, and those electrons they form this layer of electrons, and this is the channel basically, and we would like to compute the number of charges, and this is what Q channel is. And what we would like to estimate this channel to be, or the way we'll estimate the charges in the channel is to consider that there is here a capacitor. Where is the capacitor? Okay, let's take a look at this drawing here. You have the gate, which is a conductor. You have the channel here, which is also a conductor, and you have here silicon dioxide. And anytime you have two conductors isolated by an insulating material, you have created a capacitor. So in this case, we have a capacitor, and we're going to estimate this. This is a parallel plate capacitor. So you can see that this is the isolating material of the capacitor. Okay, this is here the length of the capacitor, and this is the width here of the capacitor. Okay, so if we use the model of the capacitor, then the charges on the charges of the channel can be estimated by the capacitance times the voltage across this capacitor. This is from physics course. Anytime you have a capacitor, the charges on the capacitor equal the capacitance times the voltage across the capacitor. And we've decided to estimate the channel as a capacitor. Okay, so what's the capacitance of this channel, right? What's the capacitance here? Well, the capacitance, I'm sorry, of the gate. The capacitance of the gate here can be estimated simply by, so if we look, if from physics, we said that if you have a parallel plate, okay, then the capacitance here is the area divided by the distance and the relative permittivity of the material, the isolating material. If you have, this is a parallel plate model. So let's see if we can apply this. So we say that it is the area, right? Okay, this is the area of this gate capacitance, length time width, divide by the distance separating the two conductor, which is the thickness of the oxide. This is TOX. So TOX is right here, the thickness of the silicon dioxide material, okay, multiplied by this epsilon OX, which is the relative permittivity of the silicon dioxide. So this is the silicon dioxide material. Its relative permittivity is epsilon AOX. So this epsilon AOX over TOX, we would like to create a variable for them that, okay, so this is this variable, the COX is just the division of epsilon AOX, which is the relative permittivity of the silicon dioxide, divided by the thickness of the silicon dioxide. Okay, so this is COX. Okay, so here is the capacitance. Okay, so let's pick another pin here, pin color here, so help us to trace. Okay, so you can see that we have computed this capacitance right here. Now we need the voltage here. So what's the voltage across this capacitor here? Well, it is the gate to channel voltage minus VT, because VT is essential to establish the channel. Okay, what's the gate to channel? We have not heard about this before. What's it's actually the gate? It's the voltage through the gate minus the voltage through the channel. We know that the voltage through the gate is Vg. We have seen this expression, but what's the voltage across the channel? It is actually the average voltage between the source and the drain. So for this one, what we do, we add the source, the drain, and we divide by 2. So this is the average volt on the channel, in the channel. Okay, so this is VGC. Okay, we manipulate the terms a little bit and we get VGS minus VDS over 2. So again, let's compute here VGC minus VT, and it is equal to this expression, which is what? VGS minus VDS over 2 minus VT. Okay, good. So now what we have here, let's recall what we want to do. We want to compute the Q for the channel. So we found out the C and we found out the V. Okay, all right. So now we have the Q channel. Again, what we aim to do is we aim to find out the Q for the channel, which is number of charges, and the time these charges traveling in the channel. That will estimate for me the current in the channel. Okay, so now let's go back. So now IDS is the Q in the channel over the time. We found out the Q, right? So the Q is computed already. Okay, and okay, so now we need to estimate the time. So the time, it is the time for a charge, for electron to cross the channel, equals what? The length of the channel over the average velocity of the electron. The length of the channel is L, we know that. But what's the average velocity of the electron? The average velocity of the electron equals, or the speed of the electron equals, mobility of the electron times the lateral electrical field. The lateral electrical field is VDS, the voltage between the drain and the source, divided by the length of the channel. Okay, so this is the lateral here, voltage. So there is an electrical field between here, and that electrical field, the value of it is VDS, the voltage between the drain and the source, divided by L. Okay, so this is, we plug in E here, we found V, and then we plug V back here, and this is how we find the time. And now what we do is we sort of go back and plug the time in the equation, and we have gotten the Q from the previous. So let's put everything together here. With a little bit of math manipulation, we get this expression. Okay, and basically we would like to create a variable here, beta, where beta equals mobility COX W, length of the transistor, over L, the length, I'm sorry, W, the width of the transistor, over L, which is the length of the transistor. Okay, and this is basically the expression right here, where VGT is VGS minus VT. Okay, so that is the equation for estimating the current in the transistor. And I can simplify this by saying that IDS equals beta times VGS minus VT times VDS minus VDS square over 2. This is basically the equation. Incidentally, this equation is in the linear region, as we have explained earlier. And this, by the way, this is the same as this equation. Don't be confused, except that they like to call this in your textbook as VGT. Okay, so it's the same equation. Okay, all right. So now let's move on. So again, we have seen that in saturation we need to take care of business here. But to sum up, this is the current equation for the linear and for the saturation, and we have to recall last time in the previous class we said that the current if we plot IDS versus VDS, we will see that the equation will look like something like this. Uh, Something like this, like this, like this, like this, and these are for different values of the VGS. So let's say, for example, VGS 0.5, VGS 0.7, VGS 0.9, of course all are volts, and VGS 1.1 volt. Okay, and then you can see that the current goes through the linear so this region, oops, yeah, so this is let's see if I can use so this region here, if we split it, uh, okay, so so this is linear region and this is saturation region, and the separating barrier here is when equals VDS equals VGS minus Vt. That's the separating factor. So you look at these curves here. Now someone says, well, it's not a single curve. I say, yes, not because it depends on the value of VGS. Okay, in the linear region, this is the equation. In the saturation region, this is the equation. Notice the equation in the saturation does not contain VDS. Why? Because in the saturation region, the curve is not a function of VDS. Okay, it's just a function of VGS and VT. But in the linear, you can see this VDS here, and that's why you can see that as you increase VDS, you can see the linearity. Once you get into saturation, the curve flatten off, and it is no more a function of VDS. Okay, so these are the equation. So at the off, current is 0. At the linear, VGS minus VT minus VDS over 2 multiplied by VDS with a beta, and then beta over 2 VGS minus VT square. This is in saturation, where keep in mind that beta equals mobility times epsilon OX over T OX times W, the width of the transistor, over L. Okay, as we said earlier, we would like to call this COX. Okay, so this is the beta that we are showing here in the equations. Okay, all right. All right, so here is a plot again of this is the current IDS versus, let's see if we get red color here, the IDS versus VDS, and for different values of VGS. Again, watch the region here. Watch the region. This is linear, okay, and here is saturation. Okay, when the curve flatten off, that's when it's saturation. Notice that the curve goes higher and higher for higher VGS. Okay, all right. Okay. Here's an example. He wants us to compute the values of the current, and this is something you will do in the exam. And the most important is, and we will have an example for that, is to determine this factor beta. As we said, it's equal mobility COX W over L, and from the equations you can derive. I'm sorry, from the question you can get. So, for example, W over L, he's saying that W over L equal 4 over 2 lambda. 4 over 2 lambda here means it is equals to 2. So this is it means equals to 2. And COX, it is here is the expression. It is 3.9 times the relative permittivity of vacuum air. Okay, I'm sorry, of vacuum. So that gives me what? That gives me epsilon x 3.9 times the relative permittivity of vacuum, and then this thickness here. Okay, this is the thickness. All will be given to you in the exam, and so now we get this is the COX. And how about in mobility? Well, here's the mobility, 80 right square centimeter per v times s. Okay, all of that you can compute the value of beta, which is essential in your calculation. So he says, calculate for me the current for these values. Okay, and he wants to do a plot, and this is something you can do in a program. Okay, like for example MATLAB, otherwise. Okay, but in the exam we will not ask you to draw a plot because we don't have the capability for you to run a program. We'll typically ask you to compute a single point with a specific value of VDS and a specific value of VGS. Okay, so you have to make the determination if it is linear or saturation of the transistor is off. Okay, and we'll take an example for that. Okay, now, so far the discussion happens. All what we have discussed so far is what device? The NMOS device. Well, how about the PMOS device? And the answer is we will reuse the same equations, but with the following changes. You see, for the NMOS device, we assume that the drain voltage is always higher than the source voltage. That's why the current flows from drain to source. That's what device? The NMOS device. Well, how about the PMOS device? For the PMOS device, the source has higher voltage than the drain. Has higher voltage than drain. It's the drain. Okay, so the current flows from the source to the drain. It's opposite to the NMOS. Okay. Now, the other the other change that you will notice when you address the PMOS device, that while voltages that we computed are positive for the NMOS, you will see that those voltages are negative for the PMOS. So positive for the NMOS, negative for the PMOS. Another thing, we will reuse the same equation with one simple difference. Anything less than in the NMOS will be greater than for the PMOS. Anything greater than will be less than, greater than. We will reuse the same equation, but you flip the relationship. So the first change, okay, you have to know how the current flows from source to drain in the PMOS as opposed drain to source in the NMOS. The second change, voltages are positive in the NMOS, they are negative in the PMOS. And the third change, these relationship will be flipped for the PMOS. If you take care of these differences, you can reuse the same equations that we have derived for the NMOS. You can reuse them for the PMOS. Okay, with these exception points, you can reuse the same equations. I'm familiar with other textbook that they give you a complete different set of equations for the PMOS. There is no need for that. You can use the same equations. Some textbooks use absolute value of this and absolute value of that, and they confuse the student for these things. Just use the same equations, but be careful of naming the source and the drain. Be careful that you will get negative values for the voltages for the case of the PMOS. Be careful of the switching the relations greater than, less than, between when you go to PMOS equations. Otherwise, they use the same set of equations. Okay, you can see here he is plotting current and voltages, and everything is negative for the PMOS. Another thing you will notice for the PMOS is that the mobility for the PMOS is less than the mobility for the NMOS, and that's why the current values for you get in the PMOS will be less than the current values that you get from the NMOS. PMOS device has lower current because holes mobility is less than electron mobility. So why are we talking holes? Because in PMOS device, what conducts the electricity is the holes. And if their mobility is less, then you have less current, and you will have less value of the current when you solve the equations. Okay. All right. With this, I would say, okay. With this, we will stop at this point, and we'll continue the discussion later on. Thank you.